So, good afternoon. So essentially I just threw together a few slides describing my work on hardware synthesis from domain-specific languages. So this is a work we've been doing at EPFL in collaboration with Stanford. So essentially, application developers have always had this love-hate relationship with FPGAs. So on one hand, FPGAs can achieve high performance, like Microsoft demonstrating that Bing searches can be done on FPGAs, and they actually achieved quite a good significant speed up. Now with Intel proposing to put FPGA with the Xeon processors, we expect that more application developers will have access to this technology. But the problem is that application developers lack hardware design knowledge. So we might say, okay, high-level synthesis tools, they might solve the problem, right? Well, the problem we see is that while you can provide a functional specification to high-level synthesis tools, if you want to get good quality hardware design, you need hardware design knowledge. Let me actually show you what happens. So here's a little example where you want to add up 512 integers, which are stored in the external memory, and you want to store the result back. So quite simply, you could write a C code like that, and use a high-level synthesis tool. What we see is that this code takes 27,000 clock cycles approximately to execute. Now what if I start optimizing the code? So I write a little more complex version. I start looking at the width of the memory interface, I use explicit burst transfers, I use all the pipelining and unrolling, explicitly saying where the parallelism exists, using local variables, all the transformations you need to do. Now the performance becomes 90 times faster, 302 clock cycles. So the approach is that we expect that this kind of representation is difficult for application developers to write. But for application developers, there's another approach. Instead of providing a general purpose programming language, which most HLS tools do, why don't we provide domain-specific languages? The idea is that each domain has a specific language which is tuned to the domain's requirement. Then this provides productivity because now the application developer has to use a programming language which is close to the domain they're working on. Within each domain, you can extract something called computational patterns. This is akin to what Berkeley was talking about, the 13 dwarfs, if you guys are familiar with that. And then Lawrence Livermore was talking about 7 dwarfs before that. So essentially these are patterns which capture the domain's computation. The benefit is that the computational patterns, which are like, for example, map, zip width, for each, reduce, give us a fixed set of components with which we build applications. For these fixed set of components, we can have premeditated strategies on how to optimize it and achieve good quality hardware implementations. So here's a, oops. So now with the approach of DSLs, what I can do is I can write the same computation with just one line. It says that data.sum, data is already defined as an element of 512 integers, .sum produces sum. And that performs about 74 times faster than the original implementation. So I lose a little bit on speed, but I gain a lot in productivity. To achieve this, here's the general tool flow we've been building. So it's abstract, but the tool flow starts from a functional specification written in a high-level DSL. It compiles it down all the way down to bit streams. To achieve this, in the first step, we use a high-level compiler. High-level compiler uses the domain-specific optimizations and maps the concepts of the application into well-defined patterns. So we have parallel computational patterns, which capture the parallelism in the application. We have sequential patterns, which are like classic elements of the sequential operations you have in a classic compiler. We also have control flow graph, which is the dependency between the different patterns. So vector addition is a parallel operation, that's in the parallel pattern. Normal sequential operation like addition, log, all are captured in sequential patterns. And the control flow graph captures how these things interdepend in the application to achieve the application's objective. Now, starting from this point, for the parallel patterns, since they have explicit parallelism for the FPGA, we perform hardware design. Essentially, we synthesize our hardware unit. To achieve the hardware, to make sure hardware unit is synthesized quite efficiently, we use pattern-specific code generation. We use data access analysis and optimizations. We generate a bunch of variants. I'll go into a little bit of detail of what happens here in the next slides. Now, for the rest of the code, which is a sequential pattern on the control flow graph, we synthesize a software program which essentially schedules the different patterns correctly and executes the entire application. Now, putting these two things together within the standard FPGA tool flow, we can generate complete bit streams. So that's what we have been building in the. This is a work which we presented in the FPL for 2014, so last year. So now to elaborate a little bit of what kind of hardware we generate, this is a general template for any kind of hardware we generate at the moment. So this is what we assume as a good template to start for the specific domain we were looking at. So we have a software processor which executes the sequential operations and the scheduling. We have parallel computation units which are generated from the parallel patterns. We have some shared memory created here, and we also have a wide system bus which interconnects all the units together. So that's the template for us. Now we're looking at these parallel patterns. These are the ones which are most interested in because we generate explicit hardware for these. The question is, how do we generate those, right? So for generating those, we started from parallel patterns. At the moment, our toolchain supports 4 different parallel patterns, namely the map, zip width, reduce, and for each. Each of these parallel patterns operates on collections, which is an abstract term we use for vectors, matrices, arrays, anything which is multi-element. And then, depending on what the specific pattern does, it operates on the individual elements of this collection to produce new elements. For example, in the map, each element is operated upon by a function to create an entirely new collection. In the reduce, all of the elements are operated upon to create a single value. So each pattern has its own way of computation. Then, for each pattern, we can have a premeditated strategy of how to optimize it. For example, let's just give you an example of what I mean by premeditated strategy. Let's consider a case of a single pattern where it reads elements from a data bus. So if I normally use a high-level synthesis tool without any optimization, I would probably get up one of those units, but essentially one unit taking each element at a time and producing the outer result. But if I know that I have data reuse happening, then I can probably explicitly instantiate cache here. Now the cache will make sure that the accesses can be done in the burst transfer, and I can efficiently use the data from the cache. But now if I knew how the data access pattern is, probably a cache is an overkill. Maybe I can just put a buffer manager and use a local buffer. Furthermore, if I know there's explicit parallelism, sometimes the high-level synthesis tools don't explicitly use the parallelism unless you reformat the code correctly. So I can explicitly format the code so the parallelism is completely revealed. Using all these gimmicks, we generate a bunch of different patterns. So that's essentially what we do, what I mean by premeditated strategy optimization. So here's the kind of application we write. So starting, as you can see, it's pretty high level. We have user inputs in the first 3 lines. Then we initialize a bunch of data points. This is a map operation. We find from the data points a min and a max. This is an instance of reduce. We recompute the values of the data, which is normalizing, and that's an instance of for each. As you can see, it's high level, it's entirely functional, no hardware specific details, and yet, I'll show you in the next slide, we have good performance from this. So here's a performance we get. So we use 4 different benchmarks, and the normalization is the last one. So as a baseline, we started using a software processor, a microblaze on a Xilinx FPGA. So that's the baseline, that's one. When we use just high-level synthesis without any of those premeditated optimizations, we get like a range between 1.7 and 2.3 faster, nothing more. The moment we use the premeditated optimizations, you get the green bars. So again, function specification, no hardware level details, and the tool is able to do this. The point is not that the high-level synthesis tool is bad, it's that you have to use it the right way. And giving it to a software engineer, it's quite likely they might end up in these kind of bad situations, essentially blaming the tool saying that the features don't perform well. By using the patterns, we are able to avoid these bad situations from happening and achieve therefore the good performance you can get. So that's essentially it. Thank you very much.
Thanks, Lou. Anybody have any questions? Yeah, Chris.
Are these tools available, and is there a framework for defining your own domain-specific language if we wanted to?
Yes, so what I've been using is D-Lite. D-Lite is a compiled infrastructure which Gaurav mentioned in this talk. It's an infrastructure built in Stanford. Essentially uses the concept of, it does a two-prong approach. It defines a bunch of intermediate representation, or richer intermediate representation that includes, on top of the standard sequence, the scalar operations, some parallel operations like a map, reduce, for each, and a few more. Now what they do is, each guy who wants to make a DSL has to map the domain operations to a bunch of these parallel patterns, one or more of those. Now given the parallel patterns, they have been building on backends. So they can generate code for GPUs, CPUs, and this is the FPGAs, They also can generate code for clusters. So it's a two-pronged approach. One on the DSL side, the DSL developer does it, and the other side, the compiler provider side, where he builds the backends.
Cool. Any other questions? Oh, cool. Thanks, Nitin.